These are going to be the topics that we are going to understand or look today. Kinetic theory of gases again. Then we have some ideal gas laws. Now this term ideal, this is something which is being used in physics like a lot more time. We'll be explaining what is ideal gas after the laws, and also we'll be looking at the speeds of different gas molecules. Like there are various different kinds of speeds that gas molecules possess. So we'll be looking at that also.
Mm.
So this is from where the chapter starts, like kinetic theory of gases. So in order to understand more about gases, like the physical aspect, what we did is we just framed some postulates, or the scientists just framed some postulates, which explains the behavior and the nature of ideal gas particles and how we can relate different quantities related to those gas things. So molecules of gas are generally considered to be identical, and there are different gases, you can say. So this thing can be understood by this particular like, term or explanation, you can say. Like you know that there are different type of molecules, and as well as we have different types of atoms also. So let me just start from the very basic thing. We all know that whatever type of matter we have by the element or it might be conductor, insulator, or whatever it is. So a matter, it can be an element, we can assume, and elements contains the smallest unit called atom. So if two different atoms combine of different elements, we get a molecule. Similarly, if two different molecules combine, they form a salt. And if we mix or able to mix two different kind of salts, we call that thing complex. So generally complexes, or you can say complex compounds, which you see, these complex compounds are the mixture of more than two salts, more than one salts to be precise. What I'm trying to say is that every element has a different atomic number. So the atom of the element will be different in size. So if the atom of every element will be different in size, so does the gas atoms also, the gas molecules also. So that's what I'm saying, that that's what the first postulate says, that the molecule of a given gas are identical but are different than those of another gas. The molecules of gas are identical, spherical, rigid, and perfectly elastic. In order to understand this kinetic theory, we need to understand these terms, that what is identical, what is spherical, what is rigid. So identical means the particles are going to be same. Spherical
Mhm.
means every molecule will be sphere in nature. No other shape is possible.
Mhm.
Rigid means that if a gas molecule is there, and I'm talking about a molecule only, and we somehow apply force on it. So
Mm.
rigid are that property which says that the shape of the molecule will not change over
Mm.
applying force also. So that is the thing. And perfectly elastic. So perfectly elastic is something if two gas molecules collide or they just strikes each other, the energy, shape, size, everything remains same. No change, basically, you can say. No change in any physical aspect.
Mm.
Energy, shape, size, dimension, volume, area, whatever you can think of, that should not change. Third point is the molecule of gas keep on a moving randomly in all possible directions. Like, for example, this is the very basic and important thing about gas. So if there is a gas molecule, The basic nature of gas molecule is they are very random. They do not stop anywhere. If there is a gas, we have to just think of it that the molecules of the gas will continuously moving, randomly moving in every direction. So
Mm-hmm.
we can't say that the gas molecule at any point of time is at rest. Then the speed
Mm-hmm.
of gas molecule may lies between 0 and infinity. 0 and infinity means like from literally 0 to no value or a value which you cannot even define. That much
Mm-hmm.
speed a gas molecule can possess. So these are the basic postulates of kinetic theory of gases. We are basically understanding the behavior and how the molecules of gas play their part in this universe. Next, some more postulates are there. No attractive or repulsive force acts between the gas molecule. Like for example, as we know that in this universe, or talk about solar system, all the planets are able to revolve around sun due to this gravitational force. That gravitational force pulls the planets towards the sun, and because of the velocity, they are moving in a circular path. So
Mm-hmm.
that kind of force is something we call attractive force. Gravitational force is the force which is supposed to be there between every type of molecule, every type of particle that is existing in this universe, irrespective of their mass. But for ideal gas, there is no attractive and repulsive force needs to be there. That the gas molecules should not attract each other or repel each other. They should stay where they are, or if they are moving, they should move accordingly. Next,
Mm-hmm.
the density of gas is constant. Now, this term density is something which we are going to use again and again in this chapter. What is density? You must have an idea, I guess.
Like the
All right.
mm,
Let's not talk about the physics from the physics point of view. Let's talk about from the general English point of view. What do you think? What is density? How can we define density?
like just how thick some like the volume of something. Or not volume, but
Hmm.
like how
Yeah, I got it. You know the meaning exactly. So density is something we represent that how uh, viscous liquid is, if we're talking about the density of liquid,
mm,
how brittle a solid is, not exactly brittle. In similar terms, we can explain how thick a particular liquid is. That shows that how dense it is. Like, for
mm,
example, if we compare milk and honey, so we can simply say that honey is more dense in nature as compared to the milk.
mm,
Similarly, if we talk about if you compare the density of metals, like we can say that iron is somewhat more dense than you can say sodium or potassium or even
mm,
some different kind of salt. So density in terms of physics we define it as that it is mass per unit volume. Like if we have a particular object, so if we want to find the density, what we can do is we just measure the mass of that object and divide the whole thing by the volume of it.
mm,
So that thing will give us density, and that is a measure of how dense an object is. So the density of
mm,
gas is something which is constant. Like for example, if there is a room and this room is completely filled with some sort of gas, so we will not say based upon the presence of gaseous molecules in a particular corner of a room that this particular corner is more dense. Like gas has a
mm,
basic nature that the density is constant everywhere, irrespective of the amount of gaseous molecules present there
mm,
in every point in a container. Then molecules constantly collide with each other with the wall, due to which their momentum changes. Like in order
mm.
to understand this point, let me just give you an example of gas cylinder. Obviously you have seen a gas cylinder, I guess, or didn't you? Have you seen a gas cylinder like LPG?
Yeah, I think so, yeah.
So have you observed that one thing in that cylinder? that the walls of the gas cylinder are very thick.
Yeah. Yeah.
What does it carry?
Um.
It carry gas. That gas is supposed to be the LPG.
Mm-hmm.
Still, we are creating a cylinder or or the container which is so thick, like the walls of the container is so thick.
Yeah.
We should ask that why this is. So this point
Probably.
explains, yeah. So I
Mm.
was saying that this is the reason why the wall of that container is very thick because the molecules are constantly colliding with each other as well as the wall, and that continuous collision with the walls of the container may create that situation that the container explodes. So
Mm-hmm.
in order to avoid that explosion, the thickness of the wall of the gaseous container is very huge.
Mm-hmm.
So momentum is keep on changing when they collide with each other. So this theory was given in order to explain the basic behavior of gaseous molecules, that how they react with the other particles, how they behave, how they move, what is the mass of the molecules. So all these points were basically covered by this particular theory, which
Mm-hmm.
is called kinetic theory of gases. Now, we need to understand about ideal gas because this theory is specifically based on specifically developed for ideal gas. And the interesting fact is there is no such thing like ideal gas or perfect gas exists in this world, in this earth, on this earth. It might exist somewhere else, but not on earth for sure. So
Mm-hmm.
perfect gas or the ideal gas is the gas which first of all, obeys all the laws, all the gaseous laws. We'll be looking at those gaseous laws also in this particular class. The molecules of such gases are basically of point size and there is no force of attraction between them. So this is what's assumed to be. But in reality, the molecules of gases do interact with each other and they do have force of attraction between them. So let us write something about it. So basically a gas which obeys all the laws, specifically all the gaseous laws. Like if you want to give you an idea that what a gaseous laws, so these are the gaseous laws. We're going to talk about Boyle's law. We're going to talk about Charles' law, Gay-Lussac law, Avogadro law, and Dalton's partial pressure law. So
Mm-hmm.
this law governs the physics, or you can say the whole science behind those gases.
Mm-hmm.
So we'll be talking about them also. Next point we have here is that like other gases, they are also point sized.
What do you mean by point sized?
Like you cannot compare it with even a point. Like
Oh.
gaseous molecules
Mm-hmm.
are you cannot see with your eyes, right? They are very
Mm-hmm.
microscopic. You just need an instrument to see this. So in order to explain the gases law, the ideal gas in a better way, we have constructed a small graph, a graph which relates temperature and product of pressure, volume, and temperature for a particular gas. So what we found that at different temperatures, the graphs go like that. But for ideal gas, it remains constant. So if we are looking at the graph more mathematically, this explains the behavior of ideal gas perfectly. Few more points we can add that this is the most important point to define ideal gas, the collision between the particles or the molecules of ideal gas is elastic in nature. What is elastic in nature? No loss in energy while collision, you can say.
Mm.
Also, no change in shape and size either.
Mm.
So this is what ideal gas is, and this is how we are supposed to explain it. Let's move further. Now, what is the equation of ideal gas? Equation of state of ideal gas. Now, this thing might be new for you, or it's like that you're looking it at for the very first time. But whatever we are going to see in upcoming classes, you just need to accept few things, like few
Mm.
things, as I'm saying, because it's not like that. There is no reason that how this thing came into the picture. Everything here in physics has a reason. But
Mm.
in order to explain every reason, it requires a lot of time. So sometimes I'll be saying that this is something you have already studied. It means that in previous grades, that thing might be introduced.
Mm.
So students generally do have idea that what is this, what is that, if they are studying physics continuously through to the grade 12. If you are
Mm.
not studying physics in 9, 10th, 11, so some of the things are like which you'll be like seeing for the first time, but it is not something which is not introduced in physics before. It was
Mm.
might be already
Mm.
introduced.
Mm.
Let me just give you the idea. So according to the ideal gas, what we found is that the pressure that a gas can feel or the gas can create or exert, it directly depends upon the temperature of the temperature of the gas. Again,
Mm.
the pressure is directly proportional, or you can say it is inversely proportional to the volume of the gas. Like for example, for ideal gas, if the temperature is more, pressure will be more. This is what proportionality shows, or this is something we also called direct relation. Like that, we call it inverse relation.
Mm.
So it was found that pressure of the ideal gas is directly proportional to temperature, that if temperature increases, it will increase. It is inversely related to the volume. Like for example, if pressure increases, volume must decrease. Or if the volume is increasing, pressure must be decreasing. This is something we can assume. Let me just give you another very basic example to understand this thing. If you blow air inside a balloon, what you are
Mm.
creating inside? You're creating pressure. So
Mm.
because of the pressure, the balloon size increases, right?
Mm.
So this is how you can say if pressure increases, uh, somehow you must just look at it from the outside. I'm talking this pressure acts on the atmosphere, so it's atmospheric pressure to be precise. So if the pressure is increasing, volume must have been decreased. So just assume that complete balloon. If you observe this balloon after 2 or 3 days, what do you observe generally?
Um, the volume of the like it decreases over time.
Yeah, over time, its volume, or you can say its size decreases. How? Because of the atmospheric pressure. Pressure outside is greater than pressure inside,
Mm.
which results in volume decrease. This explains this second relation. And by combining them, we came to an equation. So for pressure, I'm using P. For temperature, I'm using capital T. For volume, I'm using V. And for number of moles, I'm using small n.
Mm.
I should have it out here also. So when you see that proportionality thing and create an equation, you'll get PV is directly proportional to number of moles times temperature. The
Mm.
PV, when you remove this proportionality sign, or you can say that you were able to find the factor, how they're proportional to each other, with what factor. So you can put equality between them, and that factor is something regarded as R.
Mm-hmm.
This R is something we call real gas constant. Basically, it is a gas constant. This term is defined, or you can say calculated to explain that by what factor volume, product of volume and pressure is equals to number of moles and temperature.
Mm-hmm.
This is called ideal gas equation, and you must have used it in chemistry a lot. Like this part is something which
Yeah.
somewhat belongs to chemistry. Yeah,
Mm-hmm.
this is something more belongs to chemistry. In
Yeah.
physics, its expect is very less.
Mm-hmm.
Let's move further. So, what are the properties of ideal gas? So, those properties which we talked earlier, these are the properties, and we just want to learn them as soon as we can. So, that's why it is a name.
Mm-hmm.
So, molecules should be identical, first of all.
Mm-hmm.
Then, molecules
Spherical.
should be spherical, right?
And then rigid.
Next, we can say no, what no? Think.
Um, no elasticity. No.
No, elasticity is there. They are elastic in nature.
No.
Basically, the collision should be elastic in nature.
Mm-hmm.
I was saying no loss in energy during collision.
Mm.
So these were the few properties that made them different. Although most of the gases do behave as an ideal gas at some point of extent, like there are some, we can say, conditions at which we can make one gas behave like an ideal gas.
Mm.
But in order for this universe to create those conditions for that gas is not possible. So at one time, we can make one ideal gas, but naturally occurring ideal gas doesn't exist. This is what we have to learn.
Mm.
Now, this question should come to your mind that if such gas doesn't exist, then why we are actually studying the properties? So this thing is something I explain students like with this particular example. Assume that you want to become the ideal student of your class. So what are the qualities that you must possess? Answer it.
Mm. Leadership.
All
Like you
right.
should have a leader type of personality. Um, you should be good at communicating.
All
Um,
right.
like responsible. Hmm.
What else?
Like friendly in nature.
The most important, or you can say the ideal quality a student has that he should be honest, he should
Yeah.
be trustworthy, or he should respect the elders like a lot. He should be good at studies.
Mm-hmm.
Like these are the qualities of an ideal student. All those qualities which you were talking about, and this should be there. But if this quality is not present in one's personality, it doesn't mean that he or she might fail in life.
Mm-hmm.
Like the qualities means that those qualities which will never let that guy fail in life.
Mm-hmm.
So if you are not leader, it's completely fine. It's not like that you will be fail, you'll fail in life. So this is what ideal means here in physics. This is what I'm trying to explain. So these are the qualities that if a gas has in some sort of time, so that gas might be the best, you can say.
Mhm.
But that is something which is not possible, but we can approach, we can like somewhat apply that thing. So this is
Mhm.
what the properties of ideal gas we are studying. So if molecules are identical in nature, it would be easier for us to understand that what are the energy losses it may possess. Maybe there is no energy loss for other gas.
Mhm.
Molecules should be spherical. If molecules are spherical in nature, like most of us are, but somewhat of compounds are not spherical. They will form some irregular shape. So because of that, if they collide with other molecules, the energy will, you can say, exchanged, or it might be lost by the gaseous molecule. But that's not the case exactly. No loss in energy during collision. So if
Mhm.
this thing is there in the gas, so we might see that if the temperature of the room is somewhat there at 10 degrees Celsius, so it will stay at 10 degrees Celsius forever if the gas, there is no loss in energy during the collision. But
Mhm.
gases do lose energy in the collision, and because of that, the temperature rises over a period of time of a room if after you have turned off the AC.
Mhm.
That's why we are studying it, basically. Let's move ahead. So these are the gaseous laws. So these gaseous laws makes gases ideal. So now no gas obeys all four laws, you can say, all five laws. They might obey two laws or three laws. That's what doesn't make them ideal. So let us
Mhm.
try to understand what are these laws. So first is Boyle's law, and according to it, for a given mass of an ideal gas at constant temperature, the volume of gas is inversely proportional to its pressure. Like it is the first thing that I wrote there. You can also
Mhm.
write it as pressure is inversely proportional to volume. Also, volume is inversely proportional to pressure. So here, if I want to draw the PV curve, that's not now. So ideal gas has this thing, and you can see it here. So if M and T becomes constant, like now you must be thinking that the equation is written as PV is equals to mu RT. How this M came? So M is something which is there in the relation of mu. Here in this PPT, the mu is used to express the number of moles. Earlier, I told you as n, small n, but in this PPT, it is being represented by mu. So mu, that is number of moles, is nothing but given mass by molecular mass. So if so mu is somewhat proportional to molecular mass. So in
Mhm.
place of m, like in order to make PV constant, in order to make PV constant, we need to have mu RT as constants. If they become constant, so the product of pressure and volume it will also become constant.
Mhm.
So if it becomes constant, like somewhat we made it, the product, then P1 V1 and P2 V2. Like if we have two gases, one's pressure is P1, other's pressure is P2 in different container having different volume. So these for these two gases we can relate through this relation. But when is it possible? When temperature is constant.
Mhm.
Like if temperature is constant for these two containers, like its temperature is also T, its temperature is also T. Then we can write the pressure and volume product equals to for both of them.
Mhm.
So this is what Boyle's law says. So that's what I'm talking about, the graph part. So V is inversely proportional to P. So if P increases, volume should decrease. And this is what this graph says. So this is an
Mhm.
ideal gas. This is a basic graph for Boyle's law, you can say. Then we have multiple arrangements. Now, these arrangements are something which are completely a different topic or chapter. So I
Yeah.
can't
Mhm.
go into it. Although these are there for your help. So whenever you are studying this particular topic again in the school, so when teacher is teaching you something, though this might click that yes, I have seen it already.
Mm-hmm.
Then we have Charles' law, and according to it, volume is directly proportional to temperature. Now see, volume was initially inversely proportional to pressure. Now volume is directly proportional to temperature. Like if temperature increases, if increase the temperature, the volume also increase.
Mm-hmm.
Like can you just think of any real life situation based upon this relation that you increase the temperature, volume increased.
Mm. Oh yeah, like if you're boiling milk and you
Yeah,
increase like the hotter it gets, then the more like it'll rise up.
nice. Great example. This is first time someone giving me this particular real life example. Like when someone is thinking about volume and temperature, that it doesn't even try to focus it on daily life activities. They just went into this physics thing only that this is physics, so something like that. Everything going around you is physics. You just have to observe it that what are the actual different thing it is, how actual it is different. So if temperature increases, volume increases, just like in case of boiling milk. So again, for that thing, for two different pressure constant, like for pressure constant, the product of volume, sorry, the ratio of volume and temperature remains constant. This thing can be written as P by T is something constant. So if it is something constant, so we can write V1 by V2 is equals to T1 by T2. That
Mm.
is Charles' law. Again, the graphs. So this is the basic graph that we need to know. That if pressure is constant, so temperature doesn't increase or decrease the pressure, or you can say the pressure doesn't affect the volume change. So no response. Also, in between volume and temperature, we can simply see if temperature increases, volume automatically increases. Graph keeps on rising.
Mm.
So there are multiple ways to explain this particular situation. Next we have is Gay-Lussac's law. So this law explains that at constant volume, now we just made volume constant. The pressure of the gas is directly proportional to its absolute temperature. So again, we will going to have the same thing. P by T become constant. So P1 by T1, or you can say, P1 by T1 is equals to P2 by T2. So if you
Mm.
swap the positions, you'll get it. Next, again, we can represent the same situation with graphs. And here we are explaining pressure and temperature relation. So again, it says if pressure is directly proportional to temperature. So if pressure increases, oh sorry, if temperature increases, pressure must have increases.
Mm.
Give me another real life example from this situation where you have seen that if you increase the temperature, pressure also increase.
Mm.
If you are able to give that example, then I would say that you must have like a good interest in physics. If you are able to give that example.
You're saying like when the like an example like when temperature increases then pressure increases too?
Yeah.
Um.
A situation near you that where if you are increasing the temperature, pressure also increases.
Mm. I'm not sure.
Nothing. I can
Mm,
just think of from the kitchen's perspective.
mm, like in a microwave, maybe? Like if
Mhm.
you
No, not
microwave
microwave.
or in an
No, no,
oven.
not like.
In an oven.
No, no, no. All right, just think
Oh,
of
wait,
a
I know,
pressure
I know.
cooker.
Yeah, yeah, I was gonna say pressure cooker.
Yeah. So in pressure cooker, what you are exactly doing? You are heating it from the bottom,
Yeah.
and that vessel which is kept on it,
Mm-hmm.
there is a vessel on it.
Mm-hmm.
And
Yeah.
suddenly, when the enough temperature, when we constantly increase the temperature, the gases molecules there are getting so much thermal energy from
Yeah.
that source, which increases their motion. And because of that increased motion, what we see that pressure increases,
Mm-hmm.
and to release that pressure, this vessel has to blow.
Mm-hmm.
So that is the example where we actually witnessing this particular relation.
Mm-hmm.
Graph say, okay, all right. I guess you should try this out.
Mm-hmm.
So basically here you have to match the given options with the PQRS thing. So in the first A part, it says, let me help you. P is inversely proportional to volume. This is what this graph is representing. You can see it's pressure versus volume temperature.
Mm-hmm.
So what you can think of it? What is exactly happening here
Um,
with the volume?
well, the volume is decreasing.
Volume is increasing basically. You cannot start decreasing. So in this particular relation, what thing remains needs to constant? Temperature.
Mm-hmm.
If temperature is constant,
Yeah.
then we see such variation between pressure and volume. Let's talk about it. Pressure is directly proportional to volume. So if it is so, and
Then the
pressure is increasing with increasing volume,
no.
then basically we have to relate these problems with the graph. Here it says pressure is constant.
Mm-hmm.
It says volume is constant. You just have to match it. So volume is constant. So Q must volume is
For the
constant. It's
for the
D.
first one though, like how is the volume increasing? Because don't you read like the graph from left to right, and then it's going like downwards. So how is it increasing?
So if it is going downwards, it means initially pressure was this.
Mm-hmm.
Final pressure becomes this. Let me just show you. Initially pressure was this. Finally pressure becomes this. This is
Mm-hmm.
P1, this is P2. This is your graph. Just tell me which is greater, P1 or P2.
P2.
So if you're looking at it, what happens to the pressure? Is it increasing or decreasing? If it is going like that.
Oh, okay, then it's increasing.
Yeah. So that's how volume is increasing. Initially, whatever value of volume we have
Mm-hmm.
is way smaller than this volume obtained. So volume is increasing.
Mm-hmm.
So P should be A, temperature should be constant in B, and pressure should be constant in C.
Mm-hmm.
This, Yeah. So the next law is Avogadro law, and
Mm-hmm.
this law says that at same temperature and pressure, equal volume of all gases contains equal number of molecules. So again, for same temperature and pressure, like temperature and pressure, if they are constant, we are managed to make them constant. Equal volume of all gas, volume contain equal number of molecules. So it says volume is directly proportional to number of moles.
Mm-hmm.
You understand it?
Yeah.
So this is what this Avogadro law says. Again, condition is temperature and pressure should be constant. So just think of this that if there is an ideal gas, first of all, they have to prove this condition. V that for their volume, number of moles is constant. And Avogadro law says that for this thing to happen, temperature and pressure should be constant. So this is one such condition, and something like that. For an ideal gas to be an ideal gas, five or six conditions should be followed like that.
Mm-hmm.
That's why this gas or such gas doesn't exist even. That is the reason. But
Mm-hmm.
if we have a gas which follows all the laws, it would be miracle, which is again not possible. So this is depicting that how it goes. So number of moles should be constant, so N1 must be equals to N2. If ideal gas is there, so PV is nothing but nRT.
Mm-hmm.
So P1, for two ideal gases, I can write these two equations. It should be one. For two ideal gases, should be like this equation. So if we divide these two equations, we have an ideal gas equation for two such gases. Again, somewhat a hypothetical situation, but numericals wise, we use such equations. Let's move forward. Dalton's law of partial mixture pressure. Dalton's partial pressure mixture law. So this law is basically for those gases which are non-reactive in nature, like which gas which do not react with any other gas present around it. So according to this law, the total partial pressure of any gas mixture, like suppose this is a room, and in this room there are like multiple gases exist. So whatever pressure this each gas has,
Mm-hmm.
we know this, so we can calculate the total pressure of this room. So it is nothing but P1 plus P2 plus P3, or if there are more than three gases, I will add those gases also.
Mm-hmm.
So this is how we calculate the total pressure of a container or a room.
Mm-hmm.
Again, the condition is gases should be non-reactive, although which is not the case. They do react. So this is what this equation is. So this is the basic physics. I don't want you to go through these questions. Just remember the basic. The total pressure is nothing but P1 plus P2 plus P3, and we'll add all the remaining gases partial pressure to.
Mm-hmm.
This is how it looks. This is how we get this P is equals to P1 plus P2 plus P3 and so on.
Mm-hmm.
Small number of steps. So this is something which is maybe there in free response questions thing, that they
Mm-hmm.
do ask that how we obtain that relation. P is sum of individual partial pressures. So then we have to go through it. Let's move ahead. Now we are almost reaching towards the conclusion, or you can say. No, we are in the middle. So now average speed, root mean square speed, most probable speed. What are these things? So suppose a bunch of gaseous molecules, they are in a container, they are placed in a room, and they are moving. So somewhat the properties of collision maybe differ, and because of that, the average speed, or you can say that if there you get the different speeds of different molecules, and those speed is basically these average speed, root mean square speed. Let us try to see the significance of each type of speed. So it is a physics perspective that what is the average speed? Let me just give you a simple illustration. So there are number of molecules in a container, and all these molecules are moving randomly in any direction, whichever they saw. And
Mm-hmm.
because of that, we cannot calculate or we cannot see what is the speed of this particle, the all number of particles. So what we do is we try to calculate the average speed, and average speed is nothing but average. Like how do you actually calculate average? That is,
Mm-hmm.
and let's say it goes till Vn, like n number of particles are there. So we simply dividing it by n. That is number of gaseous molecules present there. Now there was some vector thing that how we actually represent them and how we actually write them. That which kind of bracket do we use them? We use with them is
Mm-hmm.
basically written, or you can say there with the equation, but we don't actually need to look at that. It is defined as the square root mean of the squares of the speed of the different molecules. Like root mean square speed is something like, in physics, we just uh, create this type of speed to define a particular type of, we can say, relation or something. Like it might be needed in some sort of theory to get it proved. So that's why
Mm-hmm.
we created that factor that there is some another concept like for average velocity or like instantaneous velocity. We just created some other concept like root means square speed. For this thing to be there, larger number of particles should be there, like a lot more number of particles should be there. So that's we can say that in a gaseous container, the number of gaseous molecules are like a lot. So there only we can apply it. We cannot apply it to some other type of number of particles, you can say.
Mm-hmm.
Like in future, you just apply it on the number of balls, and then it is not possible because number of balls and in comparison to the number of molecules present in a container is huge. So
Mm-hmm.
that much number is required to apply this factor. So this is
Yeah.
what we created. It is nothing but V1 square plus V2 square plus V3 square plus V4 square up to Vn square
Mm-hmm.
by n whole under root. This
Yeah.
is what VRM is. Another factor you can tell us. We do use it to explain several other factors. Next is most probable speed. To be honest, I really don't know that this particular conceptuality or you can say explanation is there in your course.
Mm-hmm.
But the topic suggests that this should be there.
Mm-hmm.
So that's why I'm covering these things. Again, most probable speed is basically so again it is from the completely physics point of view that why we have this. Although we do have or we do use it in chemistry also. So this is basically Maxwell Boltzmann curve. There were the two scientists who just worked on it and they just gave a curve. Let's go to that curve first. It is there. It is that Maxwell's law of distribution of velocities. So it is a curve for different curves at different temperature for the same kind of gas, you can say.
Mm-hmm.
So number of molecules. how they are affected with the volume, or you can say how they are affected with the velocity of the molecule. So the graph says that at 500 degree Kelvin, the most probable speed is somewhat possessed by maximum number of molecules. This is a very, again, different thing to understand. It is completely, you can say, experimental thing. So what they
Mm-hmm.
found is at minimum temperature, at lesser temperature, more number of particles has maximum speed, or you can say most probable speed,
Mm-hmm.
and somewhat less number of particles have different other speeds. Like if there is a container of a gas container, so some particles of it will have average speed, will possess. Some particles will possess most probable speed. Some particles will possess root mean square speed. Now, I guess it makes sense. So when we saw the graph of a same gas at different temperatures, so we found that at minimum temperature, most probable speed, one such speed possessing particles are maximum at what? At minimum temperature, at lesser temperature.
Mm-hmm.
Again, let us try to explain using the second curve. At somewhat 1000 Kelvin temperature, we found that the most probable particles become less, but the velocity is increased.
Mm-hmm.
And suddenly, if you increase the more temperature, the velocity more it increases. So number of particles reduces to be precise. So there are not less higher number of particles. Number of particles suddenly decreases when temperature increases. This is what this graph shows. That's what I'm saying, that these gases do possess multiple type of speeds, and one such speed is most probable speed and other. This is where we were. The particles of gas have a range of speed. This is defined as a speed which is possessed by maximum fraction of total number of molecules of a gas. Like you are understanding that what it is. Like in the gas, what speed most number of particles possess. That speed is something we call most probable speed.
Mm-hmm.
So if speed of 10 molecules of a gas are, let us understand it with an example. 1, 2, 2, 3, 3, 3. So 1 one time, 2 two time, 3 three time, 4 one time, 5 one time, 6 two time.
Oh, so
So
most of
3,
the molecules possess a speed of 3 kilometers
yeah,
per hour. So
yeah.
that's
So this is
mm,
most probable speed. So this most probable speed is calculated by this relation.
mm-hmm.
Like this factor is there because you can actually calculate it in real world. That's
Mm-hmm.
why it is here. Although it's completely mathematical thing, it's have nothing to the natural phenomena. We just found something, so we just add it to the dictionary, you can say. It
Mm-hmm.
is root of 2p times rho. P is what? P is pressure. This is rho. We pronounce it as RHO. This is pronunciation,
Mm-hmm.
and it is called density. It is a symbol of density, what we learned at the beginning. This is molar mass or molecular mass. This is mass, or specifically whatever given mass in the question. So again, some relations. I don't think so. We should go deep into it. Pressure equation. Again, these equations have like whole derivation thing,
Mm-hmm.
as it is a basically we have to cover all the things, but to be covering it like from in very detail, it's not possible in one or two class. So you can have a look at these equations. You might see this in this equation is going on in the class. Let me just help write what this equation is. So velocity RMS, VRMS is nothing but 3 times of pressure
Mm-hmm.
divided by density.
So
Like
density is
square.
also p, like lower p, lowercase p.
Yeah, you can say, but it comes in special character thing.
Mm.
So there is a special character in keyboard. We can type it. Square becomes this. So pressure we have calculated as PRMS square by 3 rho, 3 times the density.
Mm-hmm.
These are called pressure equations. We calculated the pressure here. Again, next, Maxwell's laws of distribution of velocities. We just learned it. Something to note it down. Temperature graphs drawn between molecular velocity and the number of molecules is known as velocity distribution curve. The velocities of molecule of a gas are in between zeros and infinity. With the increase in temperature, the most probable velocity and maximum velocity both increases. The temperature has a positive impact. Number of molecules within certain velocity range is constant, although the velocity of molecules changes continuously at particular temperature. So whatever number of molecules are there in that velocity range, so that velocity range is constant, and the velocity of molecules changes only if temperature changes.
Mm-hmm.
So temperature is the only factor. So that's why in summers we feel more heat. Expression for pressure for an ideal gas. We can conclude it like, what is the expression for pressure? Like, let me just give you the expression only, what expression it is. The pressure for an ideal gas. Again, this thing has the derivation part, whole derivation thing. It is nothing but 1 over 3 rho V square VRMS, which is, you just look on the previous slide. That is, this is that only. So I just want that you to revise this expression.
Mm-hmm.
Uh, you might see it. Definitely you will see it. Then again, if there are different type of velocities, so there are different type of kinetic energies as well. Because kinetic energy is nothing but half mv square. So more the number of velocities are there, so we have different kind of kinetic energy as well because of this only.
Mm-hmm.
This is something we call internal energy. This is something which is possessed by the particles of the gas only. Translational kinetic energy, molar kinetic energy, molecular kinetic energy. Again, everything is being explained and written well here. Just look at the formula, then we are good to go with the numericals and question part. This is used for the calculation part. Again, I don't know is it there or not, like this expression things. So we should just skip it, although it is there for your reference. Now, pressure and energy density. Such factor might be there, and it is nothing but energy per unit volume. Whenever we are talking about energy density, it simply means energy per unit volume. At what amount of volume possessing that energy? That
Mm-hmm.
quantity is something we call energy density.
Mm-hmm.
It is 3 by 2 times product of pressure and volume. That is it. You can remember it this way only. Now, for an idle gas to be an idle gas, those much things are required. But that is not the case. That is not something we see in this particular type of world. So here we have real gas. Practically no gas is idle at all. This is what it is written. But again, we think of a ideal thing so that we can achieve it someday.
Mm-hmm.
Just like an idle student. student 1 of them. They
Mm-hmm.
show some deviation from ideal gas behavior and are known as real gas. So it explains there are some assumptions that are made in the kinetic theory of gases that needs to be reframed or added. Interaction forces between gas molecules are considered negligible. They are not zero, they are negligible.
Mm-hmm.
Size of gas molecule is considered negligible, but practically they are not negligible. Again, they consider the size of the molecules as a point size, but
Mm-hmm.
actually they are not. So
Mm-hmm.
this is what difference between real gas and ideal gas. So it says PV is not equals to nRT. It says there must be some factor that should be included to cover that whole thing related with real gas. And
Mm-hmm.
that factor is something we represent by Z, and that Z is called compressibility factor. This is for real gas only. Now there are some cases. If Z is equals to 1, volume of both the gases will be same, real as well as ideal. Case 2, if Z is greater than 1, the volume of real gas should be greater. And if a value of Z is less than 1, the volume of ideal gas should be greater.
Mm-hmm.
So this is how this compressibility factors look at different temperatures. You can see from the curve that real gas approaches ideal gas behavior at low temperature and high pressure. So this is the condition that might be asked in, you can say, some MCQ or something.
Mm-hmm.
Now we are coming to the conclusion part. It won't take long, but it's interesting. So initially we studied a lot about ideal gas. We studied its behavior completely. Then somewhat called we realized that this is the thing which is not possible. We explained that there should be real gas.
Mm-hmm.
So in order to actually get the real gas equation, there comes up some scientist, and one such name is Van der Waal.
Mm-hmm.
He just worked upon it and able to find out what should be the equation for real gas.
Mm-hmm.
So he made some corrections in that ideal gas equation. Like what was the equation? PV is equals to nRT.
Yeah.
He made some corrections in it. First, he did pressure correction that there must be something wrong with this pressure. This is what he feels. So he did some correction. Since we have neglected the intermolecular interaction, the actual pressure of the gas will be less than the ideal pressure and should, and it was found out. So he simply said that we have completely neglected the intermolecular interaction. Like if there is a molecule, there must possess some charge, so there must be some attraction or repulsion. But we have completely ignored it, which is not possible. So he said that the actual pressure of gas will be less than ideal pressure.
Mm-hmm.
So pressure should be less. So we'll see that how he accumulated it in the equation. Let us move forward. Again, he did some volume correction that this volume is somewhat need to be corrected. So he said that we have neglected the size of the molecules, but actual volume occupied by the real gas will be different. So what he said is, in explaining the ideal gas equation, we didn't consider, or we can say we have almost neglected the size of the molecule,
Mm-hmm.
which is not the case. There must be some size, so there must be some volume, which is occupied by real gas. This is what he said.
Mm-hmm.
Some factor he introduced in this equation, PV is equals to nRT. Again, mu is number of moles. That is, I'm using to represent small n. PV is equals to mu RT. So pressure must be more as per this equation, and volume should be less.
Mm-hmm.
This is something we call a real gas equation. Like these are the factors which are there in this equation. So if I write it again, it's n square A times V square. So a factor must be there for it to become an ideal gas.
Mm-hmm.
V minus NV. Again, volume should be less. So this is what real gas equation, or we also call it van der Waals equation. So
Mm.
you will definitely see this equation. So that's all. This was about the class, and